There are two ways to combine one or more components to each other in an electric circuit. Number one, series connection. Series connection is simply combining components by connecting them to each other by one of their leads. Example is what we see here. We have resistor R1 connected to resistor R2 by just one of its leads. We have R2 connected to R1 by just one of its leads. And we have R2 connected to R3 by just one of its leads. Okay, so you can see that each resistor connects to the next with just one of its leads. R1 is the resistance felt between point A and B. R2 is the resistance felt between point B and C. R3 is the resistance felt between point C and D. The resistance felt across A and D is referred to as the effective resistance of the network, and it equals R1 plus R2 plus R3. The second kind of connection we have is parallel connection. This simply is combining components by connecting them to themselves by both leads. So an example would be this on the screen. We have R1, R2, R3, and we see each resistor combines with the next one with both leads. So we have R1 connected to the first lead of R2 and R1 second lead connected to the second lead of R2. Same with R3. So we see these three resistors are in parallel. Okay, we can have just two resistors in this configuration, and we can have much more than 2, 3, 4, 5, 6 resistors in this combination. Okay, so the effective resistance in this case is 1 over Re effective is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we'll have to simplify this and find the inverse to get Re effective. Let's go into some practical examples. So the first one we have is 3 resistors connected in series. So we have resistor 68 kilo ohms, we have 470 kilo ohms, and we have 680 kilo ohms. So we have to find the effective resistance of these resistors across points AD. We'll simply have our effective to be R1 plus R2 plus R3, and that would be 68 kilo ohms plus 470 kilo ohms plus 680 kilo ohms, and that will give us 1,218,000 ohms. Okay, and we can reduce that to 1.22 kilo ohms. So let's do this practically with resistors and see if we get exactly the same thing. Okay, so we have our resistors connected together. So this is the first one, 68k. All right, we have the next one, 470k. We see the colors. Okay, so we have the next one, 680 ohms. We now put our meter leads across the resistor to get our value, and you can see we have 1.216 mega ohms, which is approximately 1.22 mega ohms, which is what we got here. Okay, moving forward, we have the second one, which is 2 resistors connected in parallel. We have 47 kilo ohms, 47 kilo ohms. Our effective resistance, of course, is 1 over Re effective equal to 1 over R1 plus 1 over R2. Okay, so if we solve this, we would have Re effective equal to R2 times R1 all over R2 plus R1. Okay, of course, we know that one way to solve this would be we get the lowest common multiple of this, which will be R1 times R2. Okay, now R1 R2 divided by R1 will give us R2. R2 times 1 will give us R2. R1 R2 divided by R2 will give us R1. R1 times 1 will give us R1. Okay, but don't forget what equals this is 1 all over Re effective. All right, so that's what equals this. So if we find the inverse of this, okay, Re effective will have to be R1 R2 divided by R2 plus R1, which is what we got here. If we have 2 resistors, you can always go straight to use this formula to get an answer, and then we can also derive for 3 resistors, 4 resistors, as the case may be. But let's move on. So we have R2 times R1, 47k times 47k divided by 47k plus 47k, and then we have 23500 ohms, which we can write as 23.5 kilo ohms. Okay, so let's get 2 47k ohms resistors and try to see if we get same answer. And so on your screen you can see we have 47 kilo ohms, 47 kilo ohms. All right, so let's read to see, and you can see that we have 23.57, okay, which tallies with what we had here. So we move on to number 3. All right, so we have this network of resistors, and we are asked to simplify them. So you can see here we have these two, we are sure they are parallel resistors. We have these two, we are sure they are parallel resistors. So we combine this and bring them down to just one effective resistance. The same thing here, then we sum them up to get the overall effective resistance across AD. All right, so we have array effective AB, okay, AB, that's this one. It will be R2 times R1 divided by R2 plus R1. Remember what we just did previously in number 2. So we have 220 times 330 divided by 220 plus 330. And we'll have this to be 132. We keep that aside. Let's look for RF CD. Okay. So we have 132 here for A as effective resistance for AB. So we look for that of CD. So we have 220 ohms times 470 ohms divided by 220 plus 470 ohms, and that gives us 149.9 ohms. So to get the effective resistance across AD, we simply sum up these resistances to get our answer. 132 plus 510 plus 149.9 ohms would give us 791.9 ohms. So let's try to combine these resistors together to see if we can get this answer. So we have a network here, okay, so you can see we have 220 ohms here, 330 ohms here, we have 510 here, 220, 470. All right, so if we take a reading across AB, you'll see we have our answer as 131.1, which is approximately, okay, which is close to 132. Then we move to CD. If we read the effective resistance across CD, we have 148.1, which is close to 149.9. All right, so the effective resistance across AD would give us 0.784 kilo ohms. Okay, so that's 784 ohms. Okay, the difference would be because of the tolerance, okay, temperature considerations. So we'll move on to the fourth one. We have this network. We're going to find the effective resistance across AB. So we simplify this first. You can see we have 220, 330, 220 in series. You can see this is connected by one end to this, connected by one end to this. We are sure these three are in series. So we sum them up to get array effective in that position, and we're going to have 770 for this place. So we bring these three resistors down to just one resistor, and we have this configuration now, 770 ohms in parallel with 330 ohms. So we solve that. R2 R1 over R2 plus R1 gives us 770 times 330 divided by 770 plus 330, and we have our answer to be 231 ohms. We simplify them to one resistor, and we have 231 ohms in series with 1 kilo ohm and 1 kilo ohm. So we sum that up and we get our effective resistance AB to be 2231. Okay, so let's try same thing with resistors. You can see we have 220, 220, 330, 330, 1K, 1K. All right, so if we find effective resistance, we have 2.225. So that's very close to what we got. That's how we solve for effective resistance from combinations of resistors.